So here is the first problem coming in the lecture, which is telling that two blocks 1 and 2 of masses capital M and small m respectively are connected by a light string passing over a smooth light pulley as shown in the figure. I shall give you the figure shortly. The tabletop is horizontal and smooth. As the system is released, find the force exerted by, in part A, the upper half of block 1 on the lower half, and in part B, left half of block 1 on the right half. This is once again a problem of pulley block system. But the interesting part is that here we have to find out the force exerted by one part of the same block on the other part by the method of section. I put this problem in difficulty level 2 and proceed to explain the figure given here. As you can see, a part of the tabletop, here is a pulley at one corner of the table and a light inelastic string passing over the pulley is attached to two blocks. This larger block lying on the table, that is numbered as block 1 and its mass is known to be capital M. So this one's mass is capital M, and the suspended block that is numbered as 2 and its mass is taken to be small m. So they have said there is friction force is completely absent, tabletop is horizontal and smooth. Also the pulley is frictionless and the string is inelastic and massless. We have to find the force exerted by, in part A, upper half of block 1 on the lower half of the same block. So you see at the figure, I have drawn these two blocks intentionally differently. Block 1 is taken a larger block, square in shape, and block number 2 is rectangular shape to avoid any future confusion. So first of all, what we do is that as the system is being released, let us find out the acceleration with which the blocks are moving. So I'll show that in my figure itself, this original figure. This is the choice of coordinate system. Direction to the right is taken to plus x axis. Direction upward is taken to be my plus y axis. And let me also show the forces. On block 1, there is a force of gravity acting vertically downwards. There is a normal force given by the tabletop upwards. The force of tension given by the string rightwards, and under these three forces, suppose the acceleration of this block 1 is a to the right. So let me write it. Force of gravity mg, normal force n, tension force T, and the acceleration is a. That is for block 1. Coming to the block 2, here is the force of gravity and the force of tension given by the string and the acceleration downwards for this block, isn't it? So force of gravity, that is small m into g, well, assuming this string to be massless and this pulley frictionless, the tension force is the same magnitude either at this point or this point. So vectorially, let me write it as the force of T dash because of a different direction. But we understand, referring to this figure, that both the force of tension T and T dash, they have the same magnitude, because with the assumptions given, T must be having same magnitude at every part of this string. Similarly, since the case of constraint motion, the string is assumed to be taut, the accelerations of both block 1 and 2 should be having the same magnitude. So let me call this one as the acceleration A dash vectorially, but we understand that both the accelerations, that is acceleration A of block 1 and the acceleration A dash of block 2, must have the same magnitude, that is A. This is the condition for constraint motion. With this understanding, let me write down the equation for x motion for block 1. There is no requirement of writing this y motion. Anyone can see n is equal to mg. It doesn't help us because there is no frictional force present. For block number 1, taking the equation for x motion to the right, sigma fx, the only force acting is the force of tension. That must be equal to the mass of the block into its acceleration. And Similarly, for block number 2, let us write down the equation for y motion. Well, we have taken upward as plus y direction. Keeping that in mind, equation for y motion for block number 2, I'm talking of this one, is coming out to be upward force is tension, magnitude is T, downward force is gravity force, so minus mg. This must be equal to the mass of block 2 into its acceleration, that is downwards, therefore it is minus a by my sign convention. Upward is plus, so downward is minus a. So let us subtract the second equation from the first equation. We might write down that by subtracting second one from first one, you can see it's minus, this is plus, this is minus, and we can see the t's are cancelling out. We have got small m into g on left hand side, right hand side is coming out to be capital M plus small m into a, and therefore we have the acceleration of the system has a magnitude of small m into g divided by capital M plus small m. That is our first important step result. We have got block 2 is going down and block 1 is moving to the right with an acceleration of magnitude small m into g by capital M plus small m. Now with this result, let us now proceed to the first part of the question, that was the part A, and we shall now find out the force exerted by the upper half of block 1 onto the lower half. And let me show that section, method of section, little enlarged view here. This is the block 1 in square shape. I am showing the same block now in enlarged view, and suppose we divide this block 1 in imagination by this dashed line into two equal halves, an upper half and a lower half. So when we do that, of course in imagination, these two halves, we can also show it separately here on my figure. This is the upper half and this is the lower half. So what are the forces exerted by these two halves on each other, the contact forces? That is the question. So let me assume I can say intuitively that since the block 1 is moving to the right, the force exerted on the upper half by the lower half should be such that it should balance the force of gravity on this upper half as well as should provide the propulsive force for its motion to the right with acceleration of a. Because if the whole block 1 is moving with an acceleration of a to the right, it means either half of it must also have the same acceleration of a to the right, isn't it? So I can show the accelerations of both the halves also in my figure. And remember, each of these accelerations has to be a, because the whole block 1 is moving with acceleration of a to the right. And suppose the force exerted on the upper half.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.